we left in the last class. So in the last class, if you remember, we started off with signed magnitude representation, or the signed way of representing the numbers. That is, how do you represent negative numbers? So that is our basic objective. So there are three different ways of representing the negative numbers here. One is the signed representation. And the second method is your first complement method, and the third one is a two's complement method. We saw advantages and disadvantages of both the methods. The advantage of a signed magnitude representation is positive number and negative numbers binary bits will be the same, but only difference is the difference in their first MSB bit. Here, the positive numbers, your MSB bit will be 0. Your negative numbers, your MSB bit will be 1. Otherwise, rest all bits will be the same. But the disadvantage here is you have two zeros, in fact, -0 and +0. And at the same time, the disadvantage here is when you subtract two complement numbers. Say, for example, you subtract +1 and -1, you will not get 0 in case of a signed magnitude representation. Then we moved on to the ones complement representation. In ones complement representation, when you add two complement numbers, let us say -2 and +2, you will get 0, but you will get either +0 or -0. Here also the problem of having +0 and -0 existed. So in order to avoid this, we moved on to two's complement method. In two's complement method, we completely avoided the double zeros that we had in the previous two cases. And then even if we add +1 and -1, we were able to get 0. So that is why we moved on to the two's complement method. Please note that we are looking at only the binary number system. Only in binary number system, we have this ones complement and two's complement. If you consider an octal number system, then we will have 7's complement and 8's complement. In hexadecimal number system, we will have 15's complement and 16 complement. So that is how the complement system is. But immediate question arises, why do you want to have a complement number system? Again, we are going to slightly repeat what we have been seeing so far. What is the need for complement? Here, as we have been repeatedly saying, that whenever you are performing the subtraction, the computers always prefer the subtraction to be done by addition. So that is why these complement methods are most preferred, especially for your computers. There are two kinds of complements in general. I mean, in the last example, we just saw a binary number system and we said that it's ones complement and two's complement. In general, if you speak for a base R, then the two types of complement we have are, if our base is R, then we have R's complement and R minus 1's complement. So you put any value of this R, right? So if you consider the base to be R, then the two types of complement that you will be having will be 2 complement and 2 minus 1, which is 1's complement, right? And if you are having a decimal number system, you will have 10's complement and 9's complement. So, and if you take an R's complement of a number, right? We will take one example now. The general representation is R power n minus n, right? So, for example here, if you want to perform 10's complement, I have always said that perform 9's complement and then add 1 to it, you will get 10's complement. I have always repeatedly said this particular process only. But there is another process also. What is that is, if it is a tens complement, just find out the, use this particular relation r power n minus n. Now here, what is the n? N represents the number of bits to represent this particular number. Okay, so this number, how many digits you have? 1, 2, 3, 4, 5 digits you have. So it is r here is base 10. So 10 power 5 minus this 52520 you will get. So what it is, 1 followed by 5 zeros minus 52520. So this is what is your tens complement of this particular number. Why this is, at least personally it is difficult to me, is because if I subtract say 100 minus 85, I have to look for carry and borrow here. Instead, if I do 99 minus 85, it is fairly simple for me. It is 14 and I add 1 to it, I'll get 15. Right? So whereas here I have to get a borrow from here, so this will be 5, and again a borrow from this, it will be 9, and then 1, it will be 15. It's slightly, I might go wrong, so hence to avoid that, I at least personally follow a 9's complement and 1 addition. So this is for a pure integer type numbers. What if you had a decimal type number or a fractional type number? Again, what is the, how many significant bits you have? You have no significant bit, right? No integer bits. So which means that the positional weight of this particular integer is 10 power 0, right? So hence this number here, if you want to find the tens complement of this number, this is subtracted from 10 power 0 minus 0.3267. So what is 10 power 0? It is 1 minus 0.3267, which is 0.6733. Now let us take another number with a combination of integer and a fractional part. So 25, how many, what is the maximum positional weight you have? It is, this is 10 power 0, 10 power 1, and how many digits you have? You have 2 digits. Here, in this particular case, you did not have any digit here, right? You did not have any digit, hence it is 0. So here, look at the number, small n. Small n here represents the number of digits on the integer part only, right? So small n represents the number of digits of n, integer parts only. So here in this particular example, in the integer part, how many numbers are there? It is 0, hence it is 0. Here, how many digits are there in the integer part? There are 2 digits, hence it is 10 power 2 minus 25.639. So this 74.361 is the tens complement of 25.639. Okay. Okay. Similarly, this is for decimal number system. Similarly, for a binary number system, since we have already taught you a generalized expression, r power n minus n will get you the any complement that you want. Okay. So if you want the 2's complement of this number, the formula I'll write it here. It is r power n minus n. So n represents the number of digits in the integer part. So here there are 3 digits here, and what is the base of this? It is 2. So it is 2 cube minus that particular number n, 101. So 2 power 3 is 8, and 101 corresponds to 5 in decimal numbers. So 8 minus 5 is 3. So 011 is the complement of the 2's complement of this particular number. Okay, I will tell you a short trick of finding a 2's complement for binary numbers easily. Say 101 in this particular case. Always travel from your right hand side here towards this direction, right? So if you are meeting the first one, till you are meeting the first one, you copy the number as it is, and after meeting this first one, complement every bits, you will get your 2's complement. Or maybe I'll take another example here. Say for example how can you do this 2's complement in minutes is, I'll add 2 more zeros. Yeah. Now you have to travel from this direction. If you travel in this direction till you meet 1, copy the digits as it is. So which means I'm having 0 here, I'm having 0 here, 0 here, and I have met 1. Okay. So once I have met 1, after this I have to complement every bit that is following. So 0 will get converted to 1, 0 gets converted to 1, 1 gets converted to 0, 0, 1, 0, 0, 1, 0. And this is the 2's complement of this number. If you want, you can verify. Or maybe I'll do another simple example here. Okay, so let me take an example so that we can verify. Okay, this particular now. So what is the technique I said? The 2's complement will be, I have to first meet the first one here. I'm meeting the first one here. So till then I'll copy 1, 0, 0. And then rest all I will complement. So it is going to be 0, 1, 0, right? So this is the technique I said. Now let us do the normal method. What is the normal method? That is 2's complement. I have always said take 1's complement and then add 1. Let us take the 1's complement. What is 1's complement of this? This is going to be 0, 1, 0, 0. 1, 1 is the 1's complement, and I add 1 to it. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1, 0, 1, 0. Is these two numbers same? Both are same, right? So this is a shortcut which you can follow if you want to find 2's complement. Else you can always follow the standard method, that is take 1's complement and add 1 to it. Okay. Now let's go back to the method. Now we have seen the r's complement now. Similarly, r minus 1's complement, general representation. What is r minus 1's general complements? If for decimal, if for decimal r base is 10, so r minus 1's complement is 9's complement, right? So for 9's complement, the general representation is r power n minus r power minus m minus n. What is this? N again represents the same representation. That is, this particular part is the same. This part is same, similar to the previous r's complement method. Only addition here is we have minus r power minus n. Now let's focus on what is this. Again, r is your base, n is your integer part of your number n. So if I have 25.35, so the integer part of n will be here. It is 2 integers are there. So it will be base is 10. So it will be 10 power 2. That is the difference. Now what is this highlighted portion here? It is the fraction part digits. So you have to subtract. If you want to find 9's complement, then you have to subtract in addition to the base to the power, base 10 power minus the number of fractions you have. So let us take an example here. 9's complement of 25.369. So what is the expression? It is r power n minus r power minus m minus the number. So base here is 10. Number of integer digits is 2. Number minus base to the power. How many fractions you have? You have fractional bits. Digits, you have 3 fractional bits. Digits 10 power minus 3 minus what is this number? 25.369. This is a general representation. So you can use calculator to do this. So what is 10 squared? 10 squared is nothing but 100 minus 10 power minus 3 is 1 by 10 cube. Okay. So minus 25.369, and then you have to again subtract 10 power minus 3 is 0.001, right? So slightly looking complicated, right? So when you subtract this, you can add these two. You can add these two and subtract also, right? So what is 9 plus, let me add here. So what is the addition of this? This is going to be 0, 7, and then 370.25. 25.370 is the sum of these two things. And if I subtract 100 from that, what I will get? I will be getting 3, 6, 4, and 7. 74.630, which is this answer. Or again, let me tell you the shortcut. All you need to do is you need to write the nines complement of so many numbers. 99.999 minus 35.369. So if I subtract it, 9 minus 9 0, 9 minus 6 is 3, 9 minus 3 is 7, 9 minus 3 is 6, and 9 minus 5 is 4. Yeah, 9 minus 3 is 7. Where did I go wrong? Oh, it is 25. Yeah, 25. So 9 minus 2 is 7. So 74.630. So this is again, this is also a method you can follow to find the nines complement. Let us take another example here. So it is 0.3267 nines complement. Again, how many integer bits you have? You have 0 integer bits. Number of fraction bits you have 10 power minus 4, and then subtract this, you will get the nines complement. Now there is another property. A complement of a complement, you will always get an original number. You take any complement that is true. Meaning, let us take the complement of 101011, right? What is the complement of this? That is ones complement. Ones complement, it will be 0100 is the ones complement. Take one more complement, again you will get the original number, right? So you need to understand this property also. A complement of a complement will be the same number, same original number. Okay, so all right, so this is what I gave you as a shortcut. That is a nines complement. If you want to find the nines complement of a decimal number is found by subtracting every digit by 9. And if you want to get a tens complement, add 1 to it along with the nines complement. Okay, all right. So with this, let's move on to slightly the arithmetic operation of binary bits. So binary additions, I mean, this is, though it is preliminary, I'm just slightly repeating what you already know. 1 plus 1 is 0, but with a carry 1. 1 plus 0 is 1. 0 plus 1 is also 1. 0 plus 0 is 1. Now, normally here you will get 3-bit additions. So if you get a carry and then you have to add 1 and 0, here the sum will be 1 plus 1. So it is like this. 0 corresponds to the decimal 0. 1 corresponds to decimal 1. 1 0 corresponds to decimal 2. And 1 1 corresponds to decimal 3. So 1 plus 1 is 2, right? So 2 corresponds to 0 and 1. So this will be your carry here. This will be your carry bits. Similarly, 1 plus 0, which is going to be 1. So there is no carry. Let us have all three ones. 1 plus 1, the decimal value is 3. So 3 equivalent binary bit is 1 and 1. So hence the result is 1 and carry is also 1. So simple additions here. If you add, I mean, one example is shown here. 1 plus 1 is 0, carry is 1. 1 plus 1 is 0, carry is 1. And 1 plus 0 plus 0 is 1. And 1 plus 0 is 1, 0 plus 0, 1 plus 0 is 1. Right? These are very simple arithmetic operations. Is there any doubt so far in what we have taught? Okay, so now These are some of the additional things that you need to study. We will come back to this later. Okay, now let's continue. These particular portions we will come back. What is this is, these are floating point representations, right? So what is a floating point representation is, uh, in case if you are using, if you are very good at programming C and C or C++ or even Java, so you must know how your computer treats your uh, floating point numbers. What do you mean by floating point numbers? Say for example, some representations like this, instead of writing the decimal numbers infinitely, say 0.12535468840, instead of writing these particular numbers, always computer or given calculators, they represent in terms of floating point representation. What is floating point representation? Some examples are here. 1.25 into 10 power minus 5. That is, this one will be multiplied with some base and then some power will be written here. So these are the floating point representations. Computers, they will always use these kind of notations only instead of representing the large numbers uh, like this. Instead of writing 5 lakh, it always stores as 5 into 10 power 6 only. Right? So this particular part we will see it later. So which means that your computer will understand what is a sine, what is a mantissa, what is an exponent. Likewise, your registers, your computer will also have a fixed field here, right? So there will be three different fixed fields, one to represent the sign, one to represent the exponent part, right? And the other to represent the significant part. So this is your mantissa part, and normally they will have a range also, right? So significant in the sense to what precision you want to represent your uh, uh, the integer, sorry, the fractional part. Okay, so that we will see it maybe later. Yeah, we will see this particular part later, and then we will move on to our arithmetic operations. We will come back to this later, and then we will see. Okay. Right. Now, subtraction. How is the subtraction represented? It is, again, always recall in terms of decimals. 0 is 0, 1 is 1, 0, 1 is, sorry, um, 1 0. 1 0 is 2, 1 1 is 3. Okay, so always remember this so that it will be easy for you. So 0 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, right? So now 0 minus 1. 0 minus 1 is actually minus 1, right? So here, while performing the subtraction, there will be, the resultant is 1, but with a borrow of 1, right? So the negative value you are trying to represent as a borrow 1. So an example here, 100, if you subtract it from 1, so here it is 0 minus 1. So you are taking a borrow from here, and since this is also 0, you are taking a borrow from the next bit here. So it is 1 here, you have taken a borrow already. Again, here there is a 0 here, again you take a borrow, right? It is 1. So what is this equivalent to? This is equivalent to 4, and this is equivalent to 1. 4 minus 1 is 3, and you get this same binary bits. What do you mean by borrow is, borrow means borrowing 1 from the next digit. Okay, so that your 1 plus 0 will become 1 0 equivalent to 2 value. So you can also perform these subtractions by using additions, or you can perform these additions using complements also. Using, say, in this particular case, if you want to perform two's complement addition. Two's complement, normally we have already studied that it is easier to represent the negative numbers, but you can perform additions also using two's complement. You will get your result the same. For example, uh, as mentioned here, if sign is same, we can add the two numbers magnitude and give the common sign, right? What we do here, here also it is plus, here also it is plus, and the result will also be plus, right? In terms of binary also it is the same. 6 can be represented as 0110 and 13 can be represented as 1101. And this is also a positive quantity, this is also a positive quantity, though we will not write as plus here. From the 0 here we identify that this is a positive quantity. If it is 1 here, then we identify that they are negative quantities, and then the resultant is also 0, identifying that the result is also plus. And normally if you have a 8-bit structure, 8-bit capacity, then you will include this carry here, else you will not include this carry. Now, how do you add a positive number and a smaller negative number? Now, plus 13 can be represented as 0001101, and minus 6, again let us represent in terms of 2's complement. How do you represent minus 6 in terms of 2's complement? 6, you know that it is 110 is this 6 equivalent value, right? And how do you take the 2's complement value? Till you meet the first one, you copy as it is, and after that complement everything. So it is 0 1 1 1 1 1. So it is the same. So this is nothing but the 2's complement of 6, 1 1 1 1 1 0 1 0, as same as this particular number. So you add these two's complement, just direct binary addition. 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 0, and then it is a carry forward 1. So this carry keeps on forwarding here, 1 plus 1, 1, 1 plus 1, 0, 0, 0, and then you get 1. Normally this carry is represented, is ignored, the final carry is ignored, and this number, you are getting 0 here, the most MSB bit is getting 0, implying that your result is a positive number. Obviously that is true, right? If you have a positive number and a smaller negative number, as an example here, 13 minus 6, obviously this is going to be a positive number, and here you are also getting the answer as 0, indicating that your result is a positive number. And what is 111? This is equivalent to plus 7. Why did I write plus? Because I am having 0 here, indicating that this is a positive number. Now if suppose you are having a larger negative number, then how do you do? Again the procedure is the same. Plus 6 we represent it as 0 1 1 1, and minus 13, first plus 13 you represent as 0 0 1 1 0 1, and minus 13, the 2's complement, you can write directly. As I said, I told you a shortcut here. You have met first one here, you have met first one. After that you have to complement everything. So 0 becomes 1, 1 becomes 0, 1 becomes 0, 0 becomes 1, 1, 1 and 1. So you add these two things, 0 plus 1, 1, 1 plus 1, 0, 1 plus 0 with a carry here will be 0 and 1 here. And when there is, please note here, there is no carry. And at the same time, there are two things that you must observe. There is no carry here, and at the same time your first bit is 1. If your first bit is 1, then it means that your answer you got is negative. And at the same time, the number, the result that you got is in the complemented form. Okay, so since this is in the complemented form, one more time you have to take the complement of this. Let us take the complement of this. So again, take the 2's complement of this. 2's complement, how do you take the 2's complement in minutes? Till you make the first one, you will copy as it is. So first one is in the first LSB itself. So I have copied till that. After that, I will complement everything. So it is 0 becomes 1, 0 becomes 1, and rest all zeros, 4 zeros. What is this decimal equivalent to? This is equivalent to 7. And since I had 1 here, I will have the answer is -7 here, right? So in 2's complement form, because the sum follows the sign of a larger number, here in this particular case, you are having a negative number. That is why we are doing the complement once more. Okay. Now what if you have both negative numbers? What if you have both negative numbers? Then again, the 2's complement of 6 is, please note, 0, 1, 1, 0 is the actual binary representation of 6. So the 2's complement will be till 1, 0 it is copied, and then rest it is complemented. 1, 1, 1, 1. So 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0 is -6. Similarly, -13, I follow the same process. It is 1, 1, 1, 1, 0, 0, 1, 1 is -13. Now you add these two things. When you add, this is 1. So 1 represents your answer is negative. You are getting a carry indicating that you need not perform further complementing process. Okay, if you don't get anything here, if there is no carry here, then you must complement this further. Since you are getting a carry, you will ignore this particular carry. And what is the equivalent complement of this particular number? This is equivalent to 20. So in 2's complement form, it is this value is equivalent to 20. So this is how you perform the subtraction of two binary numbers. Any doubt? Any doubt? Okay. Now let us see an overflow condition. What is this particular overflow condition? We have already seen this overflow condition in some form, but we have not pointed this out. What is an overflow condition is when two numbers are added and the number of bits are required, or the capacity of the resultant solution is more, then you will have an overflow occurring, right? So this is indicated by the actual correct sign. So just let us go through this. When two numbers are added and the number of bits required to represent the sum exceeds the number of bits in two numbers, an overflow will occur as indicated by an correct sign bit. Now, as a quick example, if you see here, so let us see here. 125 plus 58 is 183. This 125 is represented as an 8-bit number, and this 58 is also represented as an 8-bit number. So 125 is given as 0111 1105, and 58 is represented as 0011 1011. When you add this magnitude part, what you get is, in addition to this magnitude part, you are getting one particular sign bit also. Here sign bit is 1, and this represents, and what is this equivalent magnitude? This magnitude corresponds to 55, and the sign bit is actually changed now. By the actual addition, your sign bit is changed. This has led to the incorrect output value. So meaning, we already know that if this is 1 here, we will point this to be a negative number, right? So this is not minus 183, but this is plus 183. So minus 183, if you want to represent, it requires 8 magnitude bits alone, right? Instead of, so 8 magnitude bits, in addition to that, one sign bit also you will require. But here, how many magnitude bits are there? There are only 7 magnitude bits are there, and there is only one sign bit is there. So the carry that is generated by adding these two gets overflowed into the sign bit, leading to a condition called as an overflowing condition. Leading to a condition called as overflowing condition. I'll tell you what is the problem here. I'm just repeating this particular part again. Now you are adding 125 plus 58. What is the resultant? This is a positive number, this is a positive number, and the resultant is also a positive number, plus 183. Now, if you add these two things, right, obviously we know that this is a sign bit. 0 represents that 125, this is a positive number. 58 here is a 0 represents that this 58 is a positive number. But what is happening here is when I added this particular magnitude alone, I got a carry here. This carry overflowed into the sign bit here. This is actually a sign bit position. This overflowed into a sign bit here, altering the actual value of your sign bit. Right. So this is the actual magnitude, but this has altered the sign bit, leading to this should have been 0 1 0 1 1 0 1 1 1 must be the right answer. But since the capacity is limited to 8 bits here, the carry portion has got this sign changed, leading to an incorrect answer. So what is this magnitude equivalent to? The magnitude here 0 1 1 0 1 1 1 is equivalent to 55. So this is giving me a wrong answer of minus 55 instead of plus 183. So why this has happened? This has happened because in order to represent 183 or minus 183, you need 8 magnitude bits. But here there are only 7 magnitude bits, and hence the carry that was generated from adding got overflowed into the sign bit, leading to an overflow condition. Now, how do you avoid this? How do you avoid this is when you are adding two positive numbers, obviously we know that their result is going to be positive, sorry. Okay, now let us look at how to avoid this overflow condition. If you want to avoid this overflow condition, first we must know when does this overflow condition will occur. When your overflow condition will be occurring is if you are adding two positive numbers, right? The result, there will be a carry that will change into a negative, as in this particular case. We are adding two positive numbers. The carry is changing the sign bit to a negative number. Similarly here, if you are adding two negative numbers, what if you are adding two negative numbers? Let me erase this particular part and then let me show you. Okay. If you are adding two negative numbers, let this be negative and this be negative. So obviously this will be one sign bit, this will be one sign bit, right? Now, if when you add this, again this particular carry will get overflowed here, 1 plus 1 plus 1. Again this will alter my sign bit, right? So leading to the positive answer. So yeah. So when you are adding two negative numbers also, the result will become positive, right? So what is the solution here is the solution that we post here is based on we have to perform this by 2's complement method only. So let us continue this particular part, how to overcome the overflow condition in the next class. Till this, is there any doubt?
No, sir.
Okay. If there are no doubts, then let us wind up today and we'll meet on Wednesday.